Module 4, Chapter 2.5 is Piecewise-Defined Functions. Recall that a function is a rule that assigns to each x value in the domain one and only one y value. The absolute value function is a simple example of a function defined by different rules over different subsets of its domain. Such a function is called a piecewise-defined function. Remember that the absolute value function is defined by f of x is equal to the absolute value of x, which is equal to x if x is greater than or equal to 0, but it's equal to negative x if x is less than 0. This is the way we write a piecewise-defined function. So, for example, if we had a piecewise-defined function defined f of x equals x plus 3 if x is less than or equal to 0, or 1/2 x squared if x is greater than 0. The way this works is the first function we're trying to find, f of negative 3, means that x is negative 3, which is less than or equal to 0. So the first part is determining which piece of the domain that it fits in, which determines which function we're going to use. So we're going to use the function x plus 3, which means if we plug in negative 3 for x, we get negative 3 plus 3, so f of negative 3 is 0. Now for the second one, we're trying to find f of 0. So the first thing we have to decide is is 0 less than or equal to 0, or is it greater than 0? Well, it's also less than or equal to 0, so we're also going to use the function x plus 3. So we get 0 plus 3, which is 3. For the C part, f of 3, we have to decide which formula to use. 3 is not less than or equal to 0. 3 is greater than 0, so this time we're going to use the second formula. So we would get 1/2 times 3 squared, which is 1/2 times 9, which is 9 over 2. Now remember, for a function, every x value can only have one y value, so it's going to be wrong if you take your x value and plug it into each of the formulas. Okay? Now let's talk about graphing these. We're going to have two separate graphs. The first one, f of x is equal to x plus 3 if x is less than or equal to 0. Remember, this is linear. Y-intercept is 3, slope is 1. So if we were looking at that, we would say, okay, it crosses the y-axis at 3. It has a slope of 1, which means you go up 1 over 1, up 1 over 1, or down 1, back 1. So this function, the graph would look like this right here. Okay, but we only want to use this graph for x less than or equal to 0. So for x right here, now because it's or equal to 0, we're going to shade in that point. We don't want, we don't want the part of the line up for x is greater than 0. That's included in a different graph. Okay, then for the second part, we've got 1/2 x squared. Well, remember, x squared is our parabola. 1/2 means we're going to take those values and scale them down by 1/2. So if we had 0, 0, 1, 1, now it's going to be 1/2. If we had x is 2, it would be 2 squared, which is 4. But 1/2 of 4 is 2. So what we're going to have is this little parabola. Now what I'm going to do is I'm going to put an open circle on 0 because it doesn't work for x equals 0. And then we're going to shade our little parabola on out like this. So the graph of this piecewise-defined function looks like this right here. Another example, x plus 1 if x is less than or equal to 2, and negative 2x plus 7 if x is greater than 2. So x plus 1 means the y-intercept is 1. Slope is 1, which means up 1 over 1, up 1 over 1. And we're wanting, so if we wanted to maybe pencil in what that graph looks like, and we're doing this for x is less than 2. Well, here's where x is 2, so we're going to include this because it's or equal to 2. And this is the graph that we're going to use for all x is less than 2. So I'm going to come up here and I'm going to erase the top part. Now the second part, negative 2x plus 7, that means the y-intercept is 7. 1, 2, 3, 4, 5, 6, 7. Slope is negative 2, which means we're going to go down 2 over 1, down 2 over 1, down 2 over 1. So you see what this graph's going to look like. But we only want, if we wanted to pencil it in, okay, but we only want to use this one for x is greater than 2, which means from here we're going to go down this way. Now you notice on this one, because we already had this point over 2 up 3 shaded in for the first graph, we can leave it shaded in for the second graph. This is what we call a continuous graph. We did not really have to pick up our pencil to draw that graph. So that's what that would look like on our graph. Okay, now let's go the other way. For the given graph, write the formula for the piecewise-defined function f. Give the domain and the range. Well, if you'll notice, the domain is all real numbers because this graph goes all the way to the left. We've got 0 right here, and then this graph goes to the right. So domain is all real numbers. Range, all the y values. Now the y values are from 0 down and just the number 2. So we could say that the range is from negative infinity to 0 union with just the number 2. So if we're trying to set up this piecewise-defined function, we're going to say that f is, now our two types of domain, first type is for x is less than or equal to 0. That's this bottom graph. The second graph is for x is greater than 0. Well, for x is greater than 0, that's easy. We know that it's a constant function, and the y value is always 2. For the first function, the part for x is less than or equal to 0, if you'll notice, this is the point negative 1, negative 1. This is the point negative 2, negative 2. This is negative 3, negative 3. This was our identity function that said f of x is always equal to x. If you can't look at that and tell, then what we do is we just pick some points on the line. We could pick 0, 0, and negative 2, negative 2, and do our slope formula and do the point slope and come up with that line. Okay, another type of function that we're going to talk about is the greatest integer function, which is usually written with these little braces. And what it says is f of x is equal to the greatest integer function of x, which is equal to x if x is an integer, and it's equal to the greatest integer less than x if x is not an integer. Okay, what that means is if we were doing the greatest integer function of 2, it would be 2. If we were doing something like the greatest integer function of 1.3, then we get 1 because 1 is the largest integer that is less than or equal to 1.3. And my advice to you on greatest integer function is always remember to round left, because when you start doing negative numbers, like if we had negative 2.4, you're looking for the largest integer that's less than or equal to x. Well, the largest one that's less than or equal to x would be negative 3. It's not negative 2 because negative 2 is greater than negative 2.4. But if you'll think about it on a number line, if here's negative 1 and here's negative 2 and here's negative 3, negative 2.4 is right here, so you always round left, which would be negative 3. Okay, so if we asked you to find the greatest integer function for -5, that means we would do the greatest integer function of -5, which is -5. Now your calculator will let you do this. Okay, so if we go on our calculator, we're going to go to Math, go over to Number. The int function is the greatest integer function. Whoops. So we're going to go up here to number 5, which says the greatest integer function of -5 is -5. The greatest integer function of 2.46. The largest integer that's less than or equal to 2.46 is 2. So if we did it on our calculator, we're going to go Math, slide to Number. Number 5 is int of 2.46, which is 2. And same thing for the greatest integer function of -6.6. It's the largest integer that's less than or equal to that, which would be -7. And don't get this confused with rounding because they're totally two different things. Whoops. So we're going to go to Math, Number. Number 5 is int of -6.6, which gives us -7. Now let's look at a word problem. Due to acid rain, the percentage of lakes in Scandinavia that lost their population of brown trout increased dramatically between 1940 and 1975. Based on the sample of 2,850 lakes, this percentage can be approximated by the piecewise-defined function f. Determine the percentage of lakes that had lost brown trout by 1972. By what year had 30% of lakes lost their brown trout? So the first question says, determine the percentage of lakes that had lost brown trout by 1972. Well, if you'll notice, 1972 lies in this range, so we're going to take x as 1972 and plug it into this formula. So f of 1972 is 32 over 15 times 19 minus 1960 plus 18. So we've got 32 over 15 times 12 plus 18, which would give us 43.6. So almost 44% of the lakes had lost their brown trout by 1972. Let's see if we can find by what year had 30% of the lakes lost their brown trout. Well, let's plug in some points and let's look. If we plug in 1940 here, we get 11 over 20 times 0 plus 7. So in 1940, 7%. In 1960, we'd get 20. 11 over 20 times 20 would be 11. 11 plus 17. So we know this formula is not going to work because this one works for the years between 1940 and 1960, which 30% would not be in this range. Let's go down to 1960 in this one. If we plugged in 1960 in this one, we get 32 over 15 times 0. So this one starts back at 18. And we said here 1972 was 43.6%. So we know it's somewhere between 1960 and 1972. So what we can do is we can come on our calculator and let's go up here. The first function is not going to help us any. So let's do 32 divided by 15 times x minus 1960 plus 18. And I'm going to go back to zoom 6 just to square this up, which I know it's going to be way above that. So let's go zoom 0. which is zoom fit. We usually go out and find us a pretty good window. Now we're trying to find where the y value is up to 30, and if you'll notice, if I go to window, this is that our x maxes go to 10 and our y maxes go to negative 4,000. So let's come down here and let's let our y max be 50. We just want to include a height of 50. Also, I'm going to go back up here to x max. We know that the year is somewhere between 1960 and 1972, so I'm just going to go ahead and enter a an x max of 1972. Okay, so there's our picture. If we want to look at a table, second table, that says that we hit, let's go in here and adjust these window sizes. We want our windows to be between 0 and 1972 for our x maxes, and we want our y's to be between, let's just say 20 and 50. Table setup, and let's change our table setup. Let's start looking at year 1960. Okay, so if we do that and go second table, in 1960 it was 18, and then by 1966 it hit 30.8. So we were looking to where the y value was about 30 and the x value, so it was somewhere between 1965 and 66. So the way the question is worded, by what year had 30% of the lakes lost their trout? By 1965 we had not reached 30. By 1966 we did. So we would say that by the year 1966, 30% of their lakes had lost the brown trout. Now you're ready to go and do your homework out of Chapter 2.5 on My Math Lab.